Namaste and welcome to the lecture on linear algebra through geometry. In the last few classes we have been looking at the idea of vectors in 2 dimension, and we looked at linear combinations and stuff. Then we followed it up with vectors in 3 dimension. We looked at linear combinations, we looked at linear transformations, we looked at what does it mean to say 2 vectors in a plane in 3D, and then we looked at what is it to say 3 vectors in a plane in 3D, and we again looked at the idea of linear independence, linear dependence and so on, and we looked at certain linear transformations. We also looked at the idea of I mean very intuitively the idea of eigenvalues and eigenvectors, and slowly we moved on to looking at the geometry of system of equations. Typically when we did it in 2D, we were trying to look at the equations, and we said that okay, we are going to look at the point of intersection of 2 lines, and or probably check whether the 2 lines are overlapping, so that you end up getting infinitely many solutions. And we also looked at a system of linear equations in 2 unknowns, 2 linear equations in 2 unknowns, where we said that okay, the lines are going in parallel and therefore they will never intersect, and therefore you will not have a solution. It is also some kind of inconsistency, it is also some kind of measurement error, that is what we had. Similar to that, we also looked at the geometry of system of equations, like 3 equations and 3 unknowns in the last class. In today's lecture, what we are going to do is we are going to look at our system of homogeneous equations, where we all know that a system of homogeneous equations is basically where the right hand side is all zeros. So we are going to look at that, and then we are going to revisit the ideas of Gauss elimination, again from the perspective of the our vectors and stuff. And we are going to look at LU decomposition, which is also the from the perspective of again the vectors, and then we are going to look at how do you decompose a matrix, a square matrix which is invertible, into a product of 2 matrices, invertible matrices, namely the L matrix and the U matrix, a lower triangular and the upper triangular matrix. So that will be the agenda for the class. We will follow it up with least square solutions, and then Gram-Schmidt orthonormalization, and of course eigenvalues and eigenvectors. We will also pay special attention to another decomposition of this matrix, where we are going to look at what is called as the QR decomposition, but that will be at a later point of time in this module. But right now what we are going to look at, we are going to look at the idea of homogeneous system of equations, and what is it to say find a solution for this homogeneous system of equations. We are going to look at again 3 equations, 3 unknowns. Let us go ahead. Yeah. So what are we going to do? We are going to look at 3 equations and 3 unknowns, and how are we going to do this? So let us consider this homogeneous system of equations. Let AU equal to 0, this is a 0 vector, be a system of linear equations, a system of linear equations in 3 unknowns. I will say a system of 3 linear equations in 3 unknowns. So what are we going to have? We are going to have this matrix which is say A11, A12, A13, A21, A22, A23, A31, A32, A33, and this is going to be my U vector, which is like say U1, U2, U3, and that is going to give me the 0 vector. So we want to find out the solution to this, and how does it I mean how do we view this geometrically, right? We all know there is something interesting. We all know that the vector u is equal to the 0 vector, that is the all 3 components being 0, that is the trivial solution is always a solution to this system of equation. Trivial solution always exists. Now what are we looking for? We are looking for a non-trivial solution, and we are going to make certain interesting observations about the I mean geometrically about this non-trivial solutions that we are going to get. Yeah. So what are we looking for? We are looking for geometrically if you actually read the equation, let us say this way, it is a11 u1 plus a12 u2 plus a13 u3 is equal to 0. Similarly, we have a21 u1 plus a22 u2 plus a23 u3 is equal to 0, and similarly a31 u1 plus a32 u2 plus a33 u3 that is equal to 0. So what are we looking for? So geometry, we are looking for that vector, let us say we are looking for that vector u for that vector u which is orthogonal to, that is the key point here. So we want to look at that vector u which is orthogonal to the three vectors, to the three vectors namely a1 is equal to, I will put this vector a1 is equal to the first row vector. So I will take it as a11, a12, a13. Then we are going to look at the second vector a2 which is basically the second row vector. We have a21, a22, a23, and the third row vector which is basically the a3 vector, which is nothing but a31, a32 and a33, right. If we write this the system of equations as such, as I mentioned, a11 u1 plus a12 u2 plus a13 u3 is equal to 0, it simply boils down to saying, look, we want that vector which is such that the vector a1 dot the u vector is 0, a2 dot the u vector is 0, the dot product of a3 with the u vector is 0, which means we are looking for that vector which is going to be orthogonal to all three of them simultaneously. So let's look at three important cases here which will help us understand this homogeneous system of equations, three equations in three unknowns. We will be able to understand it better. So let's look at geometrically. So the first one that I am going to look at is, say, case 1. Case 1, what are we going to say? We are going to say that the three vectors, the three row vectors, namely a1, a2 and a3 are all linearly independent vectors, linearly independent vectors in 3D. So what does that mean? So I am going to have something like this. I am going to have my three axes, say E1, E2 and E3. Let us assume that this is going to be my first vector, let us say A1 vector, and this is going to be my A2 vector, and let us say this fellow is going to be my A3 vector. Now we will see that there is we see that if these three are linearly independent vectors, and when you populate them in the matrix, like you look at the matrix which contains these three vectors as the row vectors, we will see that the determinant of the matrix is not 0, right. When we have three linearly independent vectors, we are going to say the determinant of the matrix A is not equal to 0 because A1, A2 and A3 vectors are linearly independent. If they are linearly independent, that means you will have a parallelepiped to be formed and the volume of the parallelepiped is not 0, Therefore, you will have the matrix A to be a matrix which is invertible, right. So, therefore, the determinant of A is not equal to 0, which means A u equal to 0, the 0 vector implies u is equal to the 0 vector, that is the only solution, is the only solution to A u is equal to the 0 vector. That means the trivial solution is the only solution, and therefore, that is the unique solution. So, the trivial solution is the only solution. Trivial solution is the only solution. Therefore, if we have 3 linearly independent vectors in 3 dimension, the only vector which is orthogonal to all these 3 vectors is the 0 vector, and that is exactly what we have seen here, right. You have 3 linearly independent vectors, truly linearly independent vectors in the sense that you will have a parallelepiped to be formed. If that is the case, then the only vector which is orthogonal to these 3 vectors, namely A1, A2, A3, these 3 vectors is precisely the 0 vector. I mean, that corresponds to the unique solution to the homogeneous system of equation, and that unique solution happens to be the trivial solution only. That is the, whenever we say unique solution to Ax equal to 0 or Au is equal to 0, the homogeneous system of equation, the unique solution corresponds to the trivial solution u is equal to 0. If there is a non-trivial solution, we all know that every multiple of this non-trivial solution will also give you right hand side is equal to 0 for Au is equal to 0, and therefore, any scalar multiple will give, which means you will have infinitely many solutions when there is a non-trivial solution to Au equal to 0. That is pretty clear to us. So, whenever we have 3 vectors which are linearly independent, and these 3 vectors corresponds to the 3 rows of the matrix A, then the only vector which is orthogonal to these 3 vectors will just be the 0 vector, and that is what we have seen here. Now, what are we going to do next? So, we are going to look at case 2, where we are going to have this case 2. What is case 2? We are going to say A1, the vectors A1 and A2, you can take any 2 of the 3 vectors to be linearly independent, and the third vector is a linear combination of these 2 vectors A1 and A2. I mean, you can take any pair, and the third vector is going to be a linear combination of these 2 guys. So, let us say A1, A2 are linearly independent, and let us say A3 vector is nothing but C1 A1 plus C2 A2. That means we have A3 to be a linear combination of these 2 vectors A1 and A2 for say some scalar C1 C2, right. Yeah. Now, if this is the case, we already know that if you have 2 linearly independent vectors in 3D, I mean, I hope all of us have this in mind, that we are going to look at the 3 dimensional space only, which means all these vectors are 3 component vectors. So, we are just going to look at that. So, if that is the case, then whenever we say there are 2 linearly independent vectors, that is A1 and A2 there, the span of this or the linear combinations, all possible linear combinations of these 2 vectors will be a plane, and since A3 is also a linear combination of A1 plus A1 and A2, that means the vectors A1 and A2, A3 will also lie in the same plane that is defined by the plane A1 and A2. So, let us look at how it is going to look the geometrically, how does it look like. So, let me take my 3 axes as usual. So, we have E1, we have E2 axis, and we have E3 axis. Now, what are we going to do? I am going to take, let us say this is my A1 vector, and let me say that this is going to be my A2 vector, and this is going to be my A3 vector. Since A1 and A2 are linearly independent, A3 can be, and A3 is in the same plane that is contained, I mean that contains both A1 and A2 vector, A3 can be expressed as a linear combination of A1 and A2, therefore A3 also lies in that plane. Now, It is very interesting. Now what we want is, we still want that vector u which is orthogonal to all these 3 vectors, but the only catch here is there are only 2 vectors. The third vector is going to be a redundant vector which is expressed as a linear combination of the other 2 vectors, which is essentially the problem that we solved when we took up 3D in the first place, where we said we have 2 linearly independent vectors and we want a vector which is orthogonal to the 2 linearly independent vectors, and that is where, if you remember, we found that the cross product of the 2 vectors, the 2 linearly independent vectors, is a vector which is orthogonal to both the vectors, right. If you take a1 and a2 to be linearly independent vectors, 3 dimensional vectors in 3 dimensional vectors, then the cross product of a1 and a2 is a vector which is perpendicular to both a1 and a2, right. So in this case, what are we going to say? So suppose if this is the case, so what does au is equal to 0 mean? So this simply means we are going to look at let us say this vector, we want a vector which is orthogonal to both the vectors, that means it is orthogonal to the plane. We want this vector to be orthogonal to the plane containing the 2 vectors which is basically namely a2 and a1, and automatically it also becomes orthogonal to the vector a3. So this is going to be my, let us say, the u vector, right. So what is the cross product? So if this is the case, let us also find out something else. If this is the case, we know that the determinant of the matrix A is 0, it will be 0. When there are 2 vectors which are linearly dependent, that means the rows are going to be, one of the rows is going to be a combination of the other 2 rows, the determinant is therefore 0. With the determinant being 0, we will trace back to what we studied in 2 dimension case. Whenever the determinant is 0, we either had the question of infinitely many solution or no solution. However, we are going to look at homogeneous system of equations here, which means we are trying to look at the case where we are dealing with only infinitely many solution, because Ax equal to 0 will always have a solution. The question is it unique or infinitely many? There is no way that we will get a no solution case at all. So the only thing that we are looking at is what is that vector which is going to be orthogonal to these 2 guys such that we get the 0 vector. And since a1 and a2 are non-zero vectors, u is going to be the cross product of these 2 vectors which is basically perpendicular to a1 and a2. So the vector, the solution now is basically solution to au equal to 0. In this case, au is equal to 0 is basically u is equal to the cross product of a1, I will say this, the u is basically the cross product of a1 with a2, and this vector is going to be perpendicular to both the vectors a1 and a2. Now we want to check if this vector is also orthogonal to the vector which is a3, because a3 is also in the same plane as a1 and a2, we just want to check that. So let us take a3, the vector a3 is going to be, let us say c1 a1 plus c2 a2. Now we want to check if a3 dot u is also equal to 0. So how do we look at that? We say that c1 a1 plus c2 a2 dot product with, let us say, a1 cross a2. Now we know that a1 cross a2 vector is basically orthogonal to both a1 and a2. So we are going to expand this as c1 a1 dot a1 cross a2 plus c2 and the vector a2 dot a1 cross a2, and we very clearly know that since this is going to be orthogonal to a1 and this is also going to be orthogonal to a3 dot u is also equal to 0. So this implies a3 dot u is equal to 0. Basically whenever you have in a 3 by 3 system, we are looking for a homogeneous system of equation, and you know that one of the vectors or one of the rows is going to be a linear combination of the other 2 rows. It is easy to find out the non-trivial solution to this system of equation. The non-trivial solution is going to be the vector u which is orthogonal to both, that means that will be the cross product of the 2 vectors. Now we have case 3. Case 3 is even more interesting because we are going to look at the reverse of this problem. So, what is that reverse of this problem? Case 3, we have, let us say the vector A2 is going to be C1 times A1 vector, and the vector A3 is equal to C2 times A3 vector, right. This is what we are going to have. So, how do we find out a solution in this case? 2 AU is equal to 0, AU is equal to 0 vector. Now, what is A vector? I mean the matrix A, the matrix is, let us say A1 vector, basically along the row, this is A1 vector. Then what I have, the second row is nothing but C1 A1 vector, and the third row is nothing but C2 A1 vector, right. In this case, if you look at the geometry, this is going to be, since all these 3 vectors are in the same direction, that means A2 is a multiple of the vector A1 and A3 is a multiple of vector I am sorry A1, this is A1, A3 is also a multiple of A1, that means all these 3 vectors are along the line passing through the origin and in the direction of the vector A1. Now, what we are asking for is, we are asking for the set of vectors which are going to be orthogonal to this vector A1. If it is orthogonal to the vector A1, naturally it is going to be orthogonal to the vector A2 and orthogonal to the vector A3, and because they are all in the same direction. So, what is it that we have? In the previous case, we had 2 linearly independent vectors. We were looking for the vector which is perpendicular to these 2 vectors, and we found that it was the cross product, that was the single vector. Basically it was along the line passing through the origin and in the direction of the cross product of the 2 vectors, we had that. Now, in this case what we have is, we have one vector and we are looking for vectors which are orthogonal to this particular vector, and we already know that in 3 dimension, if you have one vector, the set of vectors which are orthogonal to these this single vector or the multiples of this vector is going to be a plane. It is the reverse of the previous case that we looked at. So, we are going to have a plane of vectors. Okay, let us look at this. Let us take a simple example and try to understand what this is. So, let us take a simple example where let me take A1 to be this vector 1 1 1, A2 also let me take it to be 1 1 1, which means it is a 1 multiple of A1, and A3 also is, let us take 1 multiple of A1, which is 1 1 1. Now, what I want is, I want AU is equal to the 0 vector, where AU is, where A is, this implies 1 1 1, 1 1 1 and 1 1 1 times U1 U2 U3 is equal to the 0 vector on the right hand side, right. This is what we have. So, if you try to do the I mean reduced row echelon form for this matrix A, we will end up getting this. So, row echelon form of A, we get this, which is nothing but 1 1 1 1. The first row does not change, the first row is 1 1 1, the second row will become 0 0 0, the third row is also 0 0 0. So, we are going to have U1 U2 U3 is equal to the 0 vector, which is this. This is what we are going to have. Now, this means we have no pivots in the second row, there is no pivot variable in second row, there is no pivot variable in the third row, which means the variables U2 and U3 are free variables and U1 is basically a pivot variable. So, what I am going to do is, I am going to parameterize this. I am sure you would be able to recall all these things from the module 2 that we did, where we looked at solving system of equations and stuff. So, what I do is, I parameterize this free variable. I will take this U2 variable to be equal to say some t, and the variable U3 is equal to say some s. Now, what do I have? I have U1 plus U2 plus U3 is equal to 0. That is the first equation that I have, which means I have U1 plus t plus s is equal to 0. So, therefore, I have U1 is equal to minus t minus s. Therefore, what is the vector which is orthogonal to this vector u? This is going to be of the form minus t minus s. We are going to have minus t and we are going to have we are going to have T and S, T and S. I can write this as, this can be written as, which implies U is equal to minus T T 0 plus S into, or let me write this as plus minus S 0 S, which is essentially, I pull the T out, I will say T out, I am going to have minus 1 0, I mean minus 1 1 0 1 0 plus S into minus 1 0 1, right. Now, if you look at this, if you look at this vector, that means any multiple of this vector, that means the set of vectors which are obtained as the linear combination of these two vectors, namely minus 1 1 0 and minus 1 0 1, linear combination of these two vectors will be orthogonal to 1 1 1, that means the example that we have taken. So, in this case if you see, there is a set of vectors which are in the plane which is defined by minus 1 1 0 and minus 1 0 1, which will be orthogonal to that one vector which we had, which is u1, and the other the vector a1, and the other two vectors, namely a2 and a3, which were multiples of a1 and a2. Is that clear? So, what we had in the first case, we had all three vectors a1 a2 a3 to be linearly independent vectors. So, let us write that. So, case 1 we are going to look at a 3 by 3 u is equal to this. Case 1, I am going to write the rows of A are linearly independent. This means u vector is equal to 0 vector is the only solution, this also means that the three rows, the row vectors of these matrix A is going to basically get you a parallelepiped whose volume is not 0, and you actually know that if the volume is not 0, volume is actually the determinant of the matrix, and the moment the determinant of the matrix is not 0, you can invert the matrix. The moment you say you invert the matrix, you have for every right hand side B, there is a unique right hand side x such that Ax is equal to B, and in this case when you have B to be the 0 vector, then u is equal to 0 is the only solution to it. Case 2, we did this. Case 2, what did we do? We took two of the rows, two rows are of A are, let me call that, okay, two rows, I mean by two rows I mean the row vectors, okay. The row vectors are linearly independent. The third vector, the third row, or one of the rows is basically a linear combination of the other two linearly independent vectors. So, let me write this. So, one of the three vectors is linear combination of the other two linearly independent vectors, is linear combination of the other two linearly independent vectors. Please note, I made a small change here, it was linearly independent was there, but one of the vectors is linear combination. So, I changed Li to Lc. If this is the case, u is equal to A1 cross A2 is a solution to Au is equal to 0. And in this case we will have infinitely many solutions. So, basically we have a plane, the two vectors are there in a plane, you are looking for that vector which is going to be orthogonal to the two vectors. That means you are going to look for a vector which is orthogonal to the entire plane, and that vector is basically the vector A1 cross A2. We took case 3 where case 3 was the following. So, case 3 was where we had only one linearly independent row, the other rows are multiples of the only other I mean one of those rows. So, for example, here we took A1 A2 vector to be let us say C1 A1 and A3 vector to be C2 A1 vector, in which case we found that the solution to AU is equal to 0. The 0 vector is the set of vectors in a plane for which A1 vector is orthogonal or the normal, basically we will take it that way, it is orthogonal, is an orthogonal vector, right. So, this is what we have. So, geometrically we have seen the idea of solving a system of 3 equations with 3 unknowns. We could see that if all the 3 vectors were linearly independent, we said that you are going to have a volume of the parallelepiped to be non-zero. That means you actually have a parallelepiped to be formed and the volume is going to be non-zero, in which case the matrix is invertible. Therefore, you can write any B vector as a linear combination of the columns of the matrix A. And we also studied what happens if 2 of those vectors, I mean if one of the vectors is a linearly independent it is a linear combination of the other 2 vectors, in which case we said that if you have Ax equal to B, it depends on where B is. Based on that we will know whether the system of linear equations have infinitely many solutions or no solution. And in the specific case where we had the homogeneous system of equation, we took Ax is equal to 0. There again we looked at the geometry. When we have all the 3 rows of the matrix to be linearly independent rows, we said that the only vector which is orthogonal to these 3 vectors is going to be the 0 vector. If you have one of those rows to be the linear combination of the other 2 rows, then we found that the cross product of 2 rows, the linearly independent rows, the cross product of that is going to be the vector which is orthogonal to this 3 vectors, and that will form that will be the solution to AU is equal to 0. And in the third case we said that there is only one row which is linearly independent, the other 2 are multiples of each other. Then we figured out that there is a set of vectors which are there in a plane which will be orthogonal to this given single vector, I mean the vector let us say A1 and A2 and A3 being multiples of this A1. So, that is what we had. So, we understood it geometrically. Now, the question is, how did we go, like when we tried to do the Gauss elimination technique, when we did, we actually ended up getting a matrix, an upper triangular matrix from the matrix A, and then we tried to solve, instead of solving Ax equal to B, we actually solved let us say Uy is equal to some C, and then we did a back substitution to get the values of let us say x1, x2, x3. This is exactly what we did. So, the question now is, how do we get to the idea of how do we get to the upper triangular matrix through elementary row transformations, which we have already done, but then again we are going to look at it in terms of geometry. There we would have studied in terms of operations, but here what are we going to do is, what are these elementary row transformations, I mean what do they mean when you look at it in the perspective of vectors, right, and that will be the topic of discussion for the next lecture, followed by which is basically the idea of LU decomposition, followed by the idea of least squared solution, wherein which we emphasize on the least square solution when B, the right hand side B vector cannot be expressed as a linear combination of the columns of the vector A. That means you cannot solve when you have Ax equal to B, you cannot find x, there is no x which solves Ax equal to B, and therefore in which case we only get an approximate solution. So, that will be the topic of discussion for the next couple of lectures. Namaste, thank you.